So my project was about deriving vegetation layers for the Hawke's Bay region. And in my project, I got to work with this beautiful 3D point cloud that was captured by the LiDAR sensor on an aerial platform. And here you see an example of what that looks like. So I worked with the raw point cloud, and the vendor pre-classified basically already lots of features such as ground and vegetation features. So this is really helpful as a base product to derive vegetation features from it. And on my next slide, I will already show you the end result, which is the final vegetation layer for Hawke's Bay. So this is a quite comprehensive overview of what has been achieved. So I created vegetation classes, which consists of forest cover, individual trees, shelter belts, and pine forest for the entire region. I also derived extremely fine resolution raster products at 30 centimeter resolution, including the elevation models, surface models, the canopy height, low vegetation cover, and tree canopy cover. I also created really nice looking daylight and shadow layers. And all of these individual raster and vector layers are quite useful to derive information about ecosystem services, about carbon, and a range of other applications. And especially those high resolution products are quite useful to, for instance, look at fine scale features that are impossible to see at sort of lower resolution 1 meter or 5 meter ground models, such as archaeological artifacts. So this talk is, don't try to make it too technical. It should be a visual sort of tour through my workflow and how I tend to process these point clouds to, end up at this regional layer. So typically regional aerial LiDAR surveys in New Zealand are divided into non-overlapping individual tiles, a couple of 100 meters each side. And in Hawke's Bay, this leads to over 40,000 individual point cloud files, with over 1 terabyte in size. And on the northwestern end here, we have initially there was a piece missing, but it came later in. So this, was quite a substantial amount of data to work through. I use quite efficient processing on the NESI high performance compute system, which means that I can efficiently process thousands of these individual tiles in parallel on a big machine. And I want to explain to you how this is sort of generally done. So if you want to process one individual tile and you do it, you'll find out that it creates some boundary artifacts at the edges. So the way I do it, or tend to do it, I sort of merge the surrounding LiDAR tiles with the central one, and then clip it back to create a buffered LiDAR point cloud. So this is sort of how this buffered point cloud looks like with the pre-classified points from the vendor. So that's just an impression of the detail that aerial LiDAR can give you. And we've seen great examples of the derived products from Nathan and Hugh before. So that's just an example of how vegetation looks like at that scale. So the aerial survey was conducted at a minimum unit of 4 points per square meter over rural areas, and 8 points per square meter over urban areas. And the next step is then to derive elevation models. And in this case, I don't tend to use the pre-computed elevation models from LINS that are available on the LINS data service, which are extremely useful for many applications. However, for vegetation analysis and some of my work, I really aim for the highest possible resolution that you can get out of LiDAR. So this is a 30 centimeter elevation model that you can see here. And this is just a comparison of how a 1 meter rasterized product of elevation looks like compared to the finer resolution that I typically look at, which is, so on the left-hand side, you see an aerial photograph at which coincidentally, or not by chance, is at the same resolution of 30 centimeter. So I tend to use aerial imagery and 30 centimeter LiDAR raster products for many applications. So it's useful to have such a standard product to go hand in hand with aerial photography. And you can identify extremely fine scale features. For, as I said, for most applications like slope mapping or erosion control, this is not very useful because it's too much detail, and you have to downsample your data or the data set to lower resolution. But for finding artifacts or for working with vegetation studies, this resolution is really what you need, especially for also for canopy surfaces. So the next step is then to height normalize the point cloud, which means that I'm interested in the absolute height of each individual point above the ground surface. I create a surface model. This is just a hillshade, which is a nicer visualization of the surface model. And you can already identify or see some vegetation features, individual trees here. However, if you sort of either difference the surface model from the elevation model or compute the canopy height more directly from the points, you get a raster product like this, which indicates the height of canopy above the ground. I tend to use this layer to identify individual trees. So I wrote an algorithm a few years ago, which is quite efficient, working with large-scale canopy height models that can identify trees, individual trees from this canopy surface. So it basically finds the top location of trees and then segments out crown objects. And the end result is then basically a polygon vector file, which includes information about crown dimensions and the height of a tree. I also process a daylight or shadow map, which means each pixel represents the average sunlight it receives over the course of a year. So it's quite attractive looking map of the effect of individual objects on shadows. So that's also useful either for visualization, but it also can be used for ecosystem service modeling. At the end, so this was an individual tile, I just clip off the outer region, clip it back to the original extent of the LiDAR tile. So now I want to go through some of the layers I derived and just show you a few examples of how they look like and how they were generated. So the tree canopy and short vegetation layer is quite a straightforward piece of work because you can just use thresholds of, for instance, 3 meters to divide the canopy height into tree canopy and short vegetation. And you can choose your own threshold values depending on your application, what you want to extract. So a forest layer, however, is a bit more difficult because it's not directly just the tree canopy layer because that's too detailed. For forest, you're not interested in individual trees, but actually a sort of generalized view of the tree canopy layer. So I applied a few morphological operations to this tree canopy layer to broaden it and clip it back to polygons with a minimum mapping unit. In this case, it was decided to use 1 hectare. So at broader scale, this information is much more useful because it avoids having too fine individual details. At the regional scale, I computed that about 37.3% of the LiDAR survey area is thus covered by forests. And this is quite a straightforward and transparent method, which can be repeated once a new LiDAR comes in. So the individual tree layer, so at that scale, basically everywhere is a tree. However, if you zoom in, you can identify finer features. And in total, I counted 57.3 million trees, including their height and also their ground dimensions, which is extremely useful also for landslide susceptibility modeling. And this is not only computed in rural areas, but also for all of the urban centers in Hawke's Bay. So this is also quite interesting for urban studies. I should note, though, that this is only the amount of trees that are visible from above, because LiDAR can only sort of literally just scratch the upper surface of a canopy height. So it will only give you the number of trees that can be differentiated by looking top down. So anything, any shorter trees or understory trees are not captured. Then the next layer, which was quite an interesting one, is a shelter belt layer. So we were interested in mapping shelter belts for the entire region. And historically, I think there exist a few data sets and reports that used either a combination of manual mapping or sort of a few GIS operations to extract linear features from a canopy height model or from aerial photography. However, in this work, I tried out a new method that was based on deep learning, which essentially is trained on examples of what shelter belts look like, and then tries to find and identify the same features in either photography or in the canopy height model. So I created thousands of these example shelter belts, and this is just a few example photos here of the training data I generated. So these blue outlines here indicate my subjective view of what shelter belts look like and what I wanted the model to focus on. And I'll come back to that later, but this subjective decision actually is quite important because that's basically what the model tries to reproduce. And there needs to be a more clear approach on how wide, how tall shelter belts should be defined. But the model performed quite well, actually. So it could, based on the training I gave it, it produced close to 40,000 shelter belt features for the entire region. And the detail is quite astonishing, actually. So this was the first time we tried out mapping shelter belts, and I think, yeah, it gave us a quite convincing map. So the next layer is the pine forest layer. Initially, we wanted to divide the forest layer into exotic and indigenous forest. However, this is quite challenging because within indigenous forest or native bush, there's quite a lot of variety, and some exotics even look like, can be visually differentiated from the canopy height or from the aerial photograph. And so we decided to focus on pine as a quite visually differentiable feature, so that we can differentiate between pine and non-pine forest cover. So again, I trained a deep learning model, and here you can see sort of the polygon outlines that I drew by hand, just pointing the model to what pine forest looks like and what everything else looks like. So the model prediction actually gives again quite an attractive looking map and can improve my original training labels. So you see that some parts that I've missed, for instance, during the manual digitization, are captured by the model, and also improves sort of the outlines quite a bit. So that was also an interesting finding. Again, this model can then be easily applied to the entire region, and deriving or inferring over 18,000 individual pine polygons. Now, this is sort of a summary of how you can stack all the individual vegetation information on top of each other. For a complex landscape like this, you can use a range of different vegetation features that we derived from LiDAR. So in the first instance, you might want to add a layer of all the individual trees above 3 meters tall. You can add other data sets that are there, such as buildings or layers of infrastructure. Here in red, I just copied in a buildings layer. Then you can add the shelter belt layer. You can add the tree canopy layer. And on top of that, you can just simply add the pine forest layer, so you know what forest or what tree canopy belongs to planted pine or pine stands. Then you can add a short vegetation layer. And in a different project, which was run by Olivier Birch for MFE, I created a layer that produced surface water or mapped surface water from aerial photography. So this was also derived for entire Hawke's Bay, and I could just add it here as well. So this gives you basically a map of surface water, small ponds from aerial photography. However, you can just add it to your landscape view here. And if you also add the extremely fine resolution river lines from Hugh's work, you get quite a comprehensive picture of what the landscape looks like. And you can, for instance, use those ponds or information on surface water or river lines to clip or to buffer and clip around riparian and calculate the amount of riparian vegetation, number of tall trees, the number of short trees, short vegetation, or how much vegetation there is around ponds or how many trees there are within shelter belts. So that's just a brief summary of what I've done in this project. And now a few recommendations and a few learnings from this work. So again, I pointed out earlier that it's really necessary to work with clear class definitions, such as what is a shelter belt, and not just to tidy up those layers at the end, but also to tweak and to improve your training data so that the layers are actually trained on the correct class definitions. Then, yeah, it's extremely important to use existing environmental layers and these layers to derive secondary data sets and also establish sort of rule sets that can be applied to regional scales. And for vegetation change analysis, I think it's quite useful to compare sort of novel AI techniques, but also to more traditional algorithms and explore what gives consistent and defendable results. I think in this work, especially convolutional neural networks, showed some promise to work with LiDAR and give extremely fine resolution vegetation maps such as shelter belts or pine forest. So that was quite promising. These techniques can be also applied to RGB photography. So in the future, it may make sense to do the same analysis on the LiDAR datasets, but it could be very well be just applied to the RGB photography, which is captured more regularly on shorter timeframes and is cheaper. So another learning and finding from this work is that unfortunately for lots of regions in New Zealand, including Hawke's Bay, the LiDAR capture date and the capture date of aerial photography is sometimes 1 year apart or more, which means that it's extremely difficult to use the LiDAR dataset and the aerial photography at the same time for the same model because there's differences and then the model or your algorithms struggle to understand which to prefer. So there's some inconsistencies. So I really strongly encourage to simultaneously acquire both datasets. And for some studies like canopy damage or subcanopy damage in forests, it's really important to have higher density aerial LiDAR datasets because with the low resolution 4 points per square meter rural LiDAR, it's impossible to penetrate sort of deeper into the canopy and you only scratch the surface. So maybe look into under canopy LiDAR capture or extremely fine resolution LiDAR from drones or helicopters. So that's it from me.
Awesome. That
Yes.
indeed was a nice visual journey through your work. Thank you for that. Zach asked if there's any knowledge overlap of different types of forest detection, for example, pines versus native via deep learning, with the tech/logic behind the LCDB.
So yes, so it's possible to detect more species from aerial photography and also from LiDAR, or a combination of both. So I'm working on several projects that actually mapped different species from aerial photography, either from regional 30 centimeter photography or high resolution ones. So that's absolutely possible, and we've published in the past on some of them. So for instance, in rural Bararapa, we worked on one project together with the soil erosion experts to map individual trees and also map their tree species from aerial photography. So these techniques can be used to explore different species, but exotic and non-exotic comes down to the definition of what species you are interested in and how clearly they are differentiable.
Thank you. One more quick question before I pass it on to Dan. Is it possible to map/identify wetlands this way?
There's several techniques available to map wetlands, again at different scales and with different wetland types exist that can be mapped even better or worse. But there's also a recent report that we wrote for MFE, trying to investigate sort of these deep learning techniques from Sentinel-2, so satellite scale at 2 meters, to explore deep learning whether it can detect wetlands. And that's a separate piece of work. But yeah, there's quite a few options. But again, there's so many different wetland types and definitions, which it's difficult to answer.
Thanks so much.